introductory sessions to this workshop before. We have this bandit problem where in any round, and we might not even assume that we know how many rounds they're going to be, the agent is choosing a single action from a set of finite size k, and then afterwards receives a loss, or sometimes you would think about the reward setting that depends only on the action that you have picked. And that's the only feedback that we get. So it's the so-called bandit feedback. And we assume that this comes from some stochastic distribution. And if we're talking about adversaries, we might even think that the adversary selects at around t the distribution for each arm in this round. And we care right now about, in the talk, about the so-called pseudo-regret, which is the expected cumulative loss of your strategy compared to the best fixed strategy in hindsight. And now we talk about a few regimes that we have. So we have the stochastic regime, where you just assume that at every round, the expectation between any fixed arm I and an optimal arm I star is going to be always fixed to some gap. And then the corruption setting, that's similar to what we have seen before in the last talk, would be a setting where there's going to be an adversary that can arbitrarily corrupt these losses in every round. And the first one we could think about is something where the corruption has some structure, where the amount that is any arm can be corrupted over the total horizon is limited in relation to this gap. A more primitive set of corruption would be when the total amount, the total budget is given by some constant c. And even a more general setting would be to say, okay, there's going to be corruption, but actually every round is going to be corrupted, and just in expectation over time, there's going to be a gap between optimal arms and suboptimal arms. And finally, there's the setting that's fully adversarial. And in this talk today, I'm just talking about these three settings, the stochastic one, the medium one with fixed corruption, and the final one. But I just want to mention that other people have studied these other settings before, and it's not really clear that this corruption setting in the middle is really the one that we should care most about. It's more that it's something that falls out of the analysis and we can prove in the setting. And that's why I think a lot of literature started picking up on the definition of corruption, because it's just something that we can do easily here. And one thing that you might wonder about whether we need this whole research at all, because the stochastic algorithms work pretty well. And the counterexamples are kind of like, okay, we have a deterministic algorithm and the adversary can just counter it, but in practice, that's not what's going to happen. And there are also algorithms such as Thompson sampling that have inherent randomization, and people didn't even really know how bad can Thompson sampling, for example, do in practice. And this is a very simple example of showing that Thompson sampling and UCB can fail in a more realistic setting. And let's just say it's a bandit problem with a context that you don't observe. Let's say you're sending some advertisement email to somebody, you have different typewriters that can generate these emails, and then you can measure whether a user will react to this advertisement or not. And let's just assume there's some hidden confounder, the weather, that changes how well is the baseline of all these interventions that you do. But we just assume that the quality between different arms that you do, they don't even change with the context. So whether the weather is nice or whether it's a rainy day, the first one is always going to be the best, and it's the best by the same margin than everything else. So how difficult can this setting be for the vanilla stochastic algorithms that people have been using? And it's surprising how bad this actually is. So if you can, the first plot would be if this context is just choose an I.I.D, so the whole problem is an I.I.D problem, then you see this nice logarithmic curves. So the first plot is up to 10,000 time in a linear plot, and the other one is a log-log plot. And then down there you see if in a bad way an adversary is choosing this context that you don't observe, then you can completely break both UCB and Thompson sampling, that you have almost linear regret. So you almost don't learn anything at all. And so this is kind of giving you an idea why it actually matters to have robustness. And what people have been doing are using so-called adversarial algorithms. Most of them are based on the concept of follow the regularized leader, or sometimes also seen as a mirror descent algorithm, which works in the way that you, instead of keeping some mean rewards that you have by the samples, you keep unbiased loss estimators. So you have this cumulative unbiased loss estimator at any time, and you're picking a sampling distribution that is the best response given some regularization. And then you sample an arm from the distribution, you receive your feedback, and then you do importance weighting to obtain an unbiased loss estimator. This has been around for a long time. The most popular algorithm is XP3, which is the bandit version of multiplicative weight update, where you use as a regularization the unnormalized neck entropy. Another potential that has been proposed before would be Tsallis inf, that obtains the best bounds overall with the best content for this problem. And what we see now, if we plot the result of this, that these algorithms, I'm taking SP3 here, they are indeed robust to the problem, where you see that in the problem before, the one where the others are failing horribly, it's still doing well. But of course, this algorithm now has a different bound, while the stochastic algorithms, they scale with the logarithm. This is scales with square root t. So you're significantly worse in the setting where it's stochastic and nice, but you're way better in this difficult setting that are there. And so naturally, there has been this question of whether you can do both. Is there really a trade-off needed between the setting where it's adversarially difficult, or can you have an algorithm that can do both? And by the time that Sebastian Bubeck stated this open problem, there was already research into this. So there were already algorithms that were to some degree achieving this, but they were extremely complicated and they were suboptimal in some parameters. And I would say the worst thing is that the constant that you just throw under the rug because you just ignore them, they're so high that you would need a time horizon that's above anything that you would ever want to do in practice. So it's just, there's no way that there's any way of doing this. And then you might say, okay, but we always throw this content under the rug, and you just in practice reduce the confidence interval or whatever, and then it seems to work well in practice. But then you lose all the guarantees. The whole point is that you have robustness here. And so let me talk about why this has been such a hard problem for such a long time. And the reason for this is that in the adversarial case, you somehow can't get around of doing importance sampling. I mean, you might introduce some small bias that you carefully control, but in the end of the day, you're still not going to be too far away from this here. And then suboptimal arms, we know for, if you want to be optimal in the stochastic setting, you can only play them at a rate that is proportional to 1 over the gap squared times the time horizon t, to get this logarithmic regret with the right dependency on the gap. And now, if you look at this, what does it mean actually for the cumulative variance that you're getting there? It's going to be of the order gap squared t square, which means that your kind of variance is of the same magnitude as the signal that you have, because the difference in loss that you have between the optimal and the suboptimal arm is delta I times t. And so all this concentration argument that people were using, they couldn't get it to work with just this rate. They had to increase the sampling rate of suboptimal arm by at least the log t factor to get any kind of concentration going on. But then you're already suboptimal in the stochastic case. So that's kind of the reason why this has been such a difficult problem. And let me walk through what people have been doing. So there are these standard algorithms, UCB, for the stochastic problem that is optimal. There is the implicit normalized forecast by Sebastian Bubeck that uses this Tsallis entropy that I have shown earlier, that is optimal in the adversarial case with the, I'm just ignoring the dependencies on the gap, but it has the lowest term that we know of. And then there has been an algorithm, SAPO, proposed that's gonna start with an algorithm for the stochastic case, and it's just constantly running some checks by doing some subsampling of what it has seen to run some test to see whether it detects with some probability that there was a violation of the I.I.D assumption. And if this assumption is there, then it's doing an irreversible skip to an adversarial algorithms, which raises a lot of problems. For example, once we want to go away from just pure I.I.D to this, but with some corruption, this thing doesn't work anymore. And the tuning is extremely complicated, and this leads to this very large bound. So that's not practical. A more practical approach was by my supervisor, who just started from an adversarial algorithm and just injected more exploration to ensure that the loss estimator that you see in the adversarial algorithm, that they will have concentration. But the problem there is that, as I explained before, you get this additional log factors in the stochastic case, because otherwise you can't get concentration. And finally, there's an algorithm. There was an algorithm brought by Chen Yu, who's sitting here, that was the first one that used an adversarial algorithm without any additional injection of exploration, and was able to just show that it has some inherent property that's already taking care of this. And in some sense, my work was to refine similar techniques that they have been using. Okay, and finally, what we have been showing is that by just using the Tsallis inf, this then everything worked out directly. You get the optimal bounds in the stochastic case, and you have the still the optimal one in the adversarial one.
So, would there be any hope to get like a guarantee where the adversarial bound will be depend on the number of adversarial time steps, and not on, like, say, like 99% of the time steps are I.I.D, 1% adversarial?
Okay, so we do have results for this corruption budget in the middle that we have. There you can frame it like this, because the number of corruption C is obviously bounded by the number of times that you say that it's not there. But there will be bound like this. Unfortunately, the other ones settings we don't have. All right, so let's start with some intuition of why Tsallis inf. I mean, kind of at the point there, it was not obvious that one would be using this, because people have not used the Tsallis inf regularization at all since the initial paper, and we were assuming that there's a trade-off needed. And so why would you pick the one that's the optimal one in the adversarial case? Why is that the one that's in the end going to turn out to be optimal in the stochastic case? And let's first look at what XP3 is doing. And there you can see that the probability distribution that XP3 is playing from is going to be some exponential of the negative cumulative loss times the learning rate, which is somewhat proportional to exponential of minus square root t times this gap estimation, where the gap estimation right now is just the cumulative loss divided by the time. And we know from the stochastic lower bound that it's hopeless to try in the stochastic case to pull suboptimal arms at a rate lower than this 1 over gap squared times t, because if you do that, then there's going to be some probability that you're misidentifying the optimal arm. And so XP3 is kind of always trying too hard to submit to the best arm, and it's going to completely under-explore suboptimal arms. And that's why it is suboptimal in expectation, and it's also why it's very hard to analyze the algorithm in the stochastic case, because when you do more exploration than needed, then you get concentration normally, you can deal with things, but if you under-explore, then what's going to happen? How do you bound the thing? That has been hard. And now, but XP3 is actually just one member of a family of algorithms. It's called the Tsallis entropy. This is the formula for the Tsallis regularization. And it's an interpolation between something called the log barrier, which is the one that Chen Yu had been using in his paper, and the XP3 as two extreme values. And the Tsallis inf that we normally talk about is just in the middle, but this is a whole range of possible regularization functions. And now let's look at what distribution an algorithm would play when it's actually using one of these range of regularizers. And by just solving this minimization problem using KKT conditions and rearranging things, we see that the probability is proportional to some expression here. And if we plug in this middle point 1/2, then this is exactly roughly 1 over gap square times t. So apparently this special regulator, the one that was the optimal in this case, seems to, when we would have the ideal loss estimation, would give us exactly the rate that we have to play suboptimal arms of to ensure that we don't over or under explore suboptimal arms. That was the starting point of why I started looking into exactly this algorithm, because sometimes people ask me this. And the next step that you should be doing, if you have an idea of what might be the algorithm, just run experiments. And if you run experiments with exactly this algorithm, you see it seems to work perfectly fine. So not only does it has this nice logarithmic curve in the nice setting, in this one hard setting that I hear, it even has a logarithmic curve there, because this setting is actually a simpler setting that we would now even call a stochastic setting, when you have this, when you have the gap at any round just being constant. That's all what you need. But you also have the guarantees in the adversarial setting. So the question is, why have people only been able to prove a bound that scales with square root t, when obviously, based on the experiment, it's doing so much better? So the next step was to look into the details of the analysis of what's happening here. And this is a version with adaptive learning rate, which is something that we need here because we want to have the probabilities growing with small t instead of capital T. So we have we just adjust the standard analysis for FTRL that you can see, for example, in the Bandit book, just for the setting where you have adaptive learning rates that is non-increasing. And then we have these two terms that you have seen in the initial talk by Haiping Luo, which is the penalty term and the stability term. The penalty term, kind of you pay for having regularization because you're taking longer to convert towards the best one. And the stability is kind of something where you pay for making big changes, which getting better when you have more regularization. And we're looking into the stability term in detail because that's a term that is harder. This df that I have here, that is the Bregman divergence. I hope you all know what the Bregman divergence is. But let's look at this first step stability term. It doesn't look exactly like the one that was Haiping was proposing there, was showing there, because it was something that depends on the norm at the local point. But I show you how we get there. So the definition of this W tilde that you have there is that it's the maximum over everything in the action set of the current step loss minus as a regularization, the Bregman divergence from the last time step that we have. And this Bregman divergence, as long as you're around the term WT, which you need to be careful about this, but here you kind of can ensure that you're always around there. It's just going to be something roughly the local norm at this point. So basically, you're optimizing here something similar to something that's regularized by the quadratic term. And now optimizing over a constraint set is always hard. So let's just get rid of the constraint set. We're optimizing over everything in RK. And now, there's also what you could do with your two first Cauchy-Schwarz approximation over there. And then with arithmetic geometric mean, you can bound this expression by this norm. So the last line is what Haiping had been showing you in one of the introductory talks. And now the problem here is when this is not good enough, because when you actually plug in the expectation over this, the norm that you see down there is going to scale in each dimension with the probability to the 3/2. Your loss estimator is 1 over the current probability. If you take the expectation, you get the sum over the square root of the current probability to play. And even in the best case, when everything is concentrated just on one single action, this term is already as large as 1 over square root t. So if you sum this over all time steps, you're ending up with a bound of square root t. On the other hand, the worst case that you have is the distribution is uniform. You get a square root k over square root t, which leads you to the optimal adversarial bound. Now the question is, which step in this whole analysis is not tight? Because we know from the experiments, in the stochastic case, it's not tight. So something must be wrong there. So you might assume that maybe it's a Cauchy-Schwarz step, because that's kind of a very worst case bound that you can get, or maybe it's the arithmetic geometric mean. But actually, because you have this maximization step in front, these things are actually tied here. There's nothing you can gain. The point where you lose is when you do the change from the optimization problem, from the constraint set to the unconstrained set. That is where actually things suddenly are not, where the things have not been tied. So what can you do on the step instead to make it tighter? Well, the idea is that you basically use something similar to a Lagrangian approach. So because this thing right now is in the simplex, that would mean that whatever you would add to the loss estimator, that it's a constant vector, it wouldn't change the optimization problem at all, because then you just add a 0 there, because both WT and V are in the simplex. So that's exactly what we would be doing here. So instead of just taking the maximization about the term that we had before, we're adding some constant of a vector that has just all the one values there. And this is kind of, if you optimize now over C, that would be equivalent to solving the constraint problem. You need to be a bit careful that you can't set C too high, or otherwise this first step that you're doing here from the Bregman divergence to this normal approximation would break. But let's just assume that this is fine for now. And what can you do with adding this term? And what it turned out that what you can do, and you can't do more, unfortunately, is that you can, in the sum where you had earlier the sum over all the probabilities, you can cancel out one term. The way you do this, for example, is to just say, okay, I have my one that I want to cancel out. If this one was the one that was played, I just remove. So first of all, I could say, if the one that I want to remove, if the probability is smaller than 1/2, then I can bound it by some constant factor of this sum anyway. So I only need to care about the case where the one I want to remove is going to be very large. But if it's large, then the loss estimator that I have is going to be small when this one is picked. And then I just set C to the value that I cancel that one out. And then by just doing this argument, it's relatively easy to see that I can always eliminate one. If you're a bit more fancy and you just try to do this approach of really optimizing C based on the current arm at every time step, you still don't get anything much better. You just maybe get better constants. And now let's continue with this. So let's just assume the other term that we have seen, the penalty term, you can do the same thing. There is fairly easy, so I don't show you how, but there you can exactly do the same thing. You can remove one contribution of one arm. Now, what have you gained here? I mean, you still don't really know how to bound things, right? Because we don't know how is actually the distribution of WT looking like. That's the hard thing here. We don't have concentration, we have nothing, we don't know what this. And if you just take the worst case, and we see this as an optimization problem, then now the solution would be you put all the weight on everything but the one that you have removed, and you still have a bound that scales somewhat with square root T. So there is another step missing here. And so what is missing is that we actually know something about the regret, because in the stochastic case, we know the regret is exactly the sum over this probability that we play suboptimal arms times the gap. And now, since we have an upper bound on this that was scaling there, we have this nice expression here. So people who just see this and are familiar with the technique, they might see immediately, okay, you just do arithmetic geometric mean, you rearrange things and you're done. But if you don't see this, what I would always suggest people to do is to just say, okay, let's see that an optimization problem. How bad can it actually be? This is something that's very often very useful to write down. And if you actually solve this optimization problem, you get exactly to the point where you see the regret is bounded by the logarithm over the gaps, which is the optimal ratio in the stochastic case. And now we come to the point where we actually start talking about corruption, because the nice thing about this whole analysis like this is that we get corruption completely for free. All that changes is that in the corrupted case, our regret is not equal to the sum of its gap, but it is lower bounded by the sum over the gap by the probability minus that corruption budget that we had. And now we can still do exactly the same thing. We formulate this as an optimization problem. We plug everything in, and we just get this term there that depends on the corruption. It's not even linear in the corruption, which is nice. And it can handle, so even in the case where everything is fully corrupted or almost fully corrupted, we don't even need to go to the adversarial bound, but we still have something reasonable here. And now you see why it has been so hard and we haven't managed to deal with the other settings that I proposed. For example, the case where we have the structured corruption, where the corruption is in the way that the gaps still are preserved over time. So the corruption can only scale always with the gap of an arm times the time. Until then, well, this whole argument here that you have this lower bound, you can't do this anymore. So the best that I know there, what you could be doing in the case, let's say over t times gap rounds, you have exactly a corruption of 1. You could just take this this corruption level with non-overlapping different sets, and you take a randomization over the corruption, and this is your environment, and this environment is stochastic, going to have a bound, and because it's non-negative, you get a bound for each of them, which is still very bad because then you get some extra factor, but you have to go completely out of your way because this analysis doesn't really work in this setting. And yeah, that's but on the other hand, it has been extremely successful. So people have been working on exactly this principle. It has been extended to combinatorial semi-bandits. The key idea there has been to just use some hybrid regularization, that you deal with different cases in there, and you have right. And then for uncoupled exploration, where let's say the feedback that you get is not from the same arm as the one that you play. So you can play one arm which loss you suffer, and you can pick another arm whose feedback you get. So there you can get best of both worlds by just using a different alpha value in the Tsallis entropy. It's still something that is different from XP3, is different from the one is somewhere between Tsallis and XP3. Then you can get simultaneous second and first outer bound. That has Iter et al. Had shown this. It's an extension of the broad algorithm that Chen Yu had, where the main idea is to use additionally optimistic FTRL and then running a top level algorithm optimizing the optimism that you add. In reinforcement learning with adversarial rewards, there the main idea was when earlier I was adding in the optimization step this Lagrange factor with the C times some constant vector there, it was to have an even better shift based on the fact that we have some Bellman equation and we have even a larger set over the optimization that wouldn't change, and doing optimization there. Then people have extended this to bandits with graph feedback, which is again a hybrid regularization, and we now have a new result with bandits with delay. So this analysis has been extended to many settings, and the nice thing is in each of these settings, we always get corruption robustness for free without needing to change anything in the analysis or even care about it, because we just always have the self-bounding technique, everything there. But the drawbacks, as I mentioned throughout the talk already, are that one thing is we don't get high probability bounds with this, because it just everything relies on expectation. We don't even try to get concentration. We don't know. We don't even know whether if it's purely stochastic, if it's then at least high probability. Don't know. Another thing was it was really hard to deal with the case of multiple best arms, because as I've told you before, I'm eliminating one arm. But the thing is, I can only eliminate one arm. And if I have two optimal arms that have exactly the same loss, then the probability mass will be somewhat distributed to them. And then the stability term will grow with square root t. And in experiments, you see the stability really grows in square root t. The reason why the overall regret is still fine is that the penalty term that I was not talking about today is going to be negative in that setting. But it has been extremely technical to show that the negative term canceled out exactly the positive term. This has been done once in 2021 for the case where we just have bandits, but nobody has ever done this for any of the other settings because it's just extremely technical. People wouldn't care about it. You just always assume, okay, there's one unique best arm, and you do it with this. And maybe you say, okay, in bandit it works. It will probably work as well, but it is just going to be not worth it to try. Then these other intermediate regimes that I was showing. People have running experiment on it. They give, we haven't found any example where it would break, where Tsallis inf would not have the logarithmic regret anymore. So it seems to be that this algorithm is robust in the other settings as well. But we just have no idea how to prove it, because this analysis is so reliant on having this per step property. And there's something going on that you would need to aggregate over several time steps, and we just don't know how to do it. And finally, one thing where we couldn't extend it is linear bandits, where again, we have an algorithm that generalizes one of the base algorithms, the one with the log barrier, towards linear bandits. We can run experiment, it worked in the experiment, it has logarithmic regret, but we can again show that in very bad cases, the stability term can actually be larger than what we need. And we don't know how to deal with it in the analysis. We only know that it seems to work. And so I'm just saying that even though there's a lot of success with this analysis, there's still issues that we can't figure out how to do. Thank you very much. Any questions?
Questions?
Yeah.
The bubble he gave a square root of C times lefty over down.
Yeah.
So I guess if I think about worst case things, this is not square root of T, right? Well, you give a square root of T there, because you think of dot C being T and the gamma being 1 over square root of T. Right. So like, is there a better interpolation of the conformity that actually?
Yeah, so there has been, I think, a paper published where they, I mean, you can do this optimization problem a little bit better, where you can show that if you're in the regime where T approaches something of T over log T, then you can even improve this term down here, and you, instead of a log T, you, I think, get a log T or something. And so the bound is getting actually better when you're getting close to this regime. This is more the simple way of proving it when C is reasonable. And in the end, you still have the adversarial regret bound. So you know that at the end of the day, you have a bound of square root KT. And the question is, do you really care so much when you have already corruption of the level of T divided by log T? Do you care whether it's going to be square root KT or whether square root KT over log of T is? Yeah.
The comment you made about high probability bounds, was the place where it broke down that right in the beginning when you did the stability penalty decomposition, that's an expectation? Or?
Yeah, so exactly. So basically, you always do the stability already, you do over expectation. So when you have.
Do we know decomposition of the actual regret itself, rather like the random variable of the regret rather than expectation?
So you can change adversarial algorithms to be robust to the regret itself, but it normally relies to add even more exploration on the arms to control this variance term that you're getting. So if you inject something like 1 over square root T exploration with the right, or like some implicit bias that is similar to this, then you can get high probability bound on the actual regret. But you always have bound that already square with square root T when you're doing it. So yeah, but the thing that you might hope for is having high probability bound when it is stochastic. Yeah.
Yes, for the high probability bound, for the adversary setting, I do have this paper where he does this optimistic modification, right? And then you can have the high probability bounds just for the adversary setting. So I don't know whether people try to look into whether if you consider that modify, like I think that that modification might actually be necessary to get high probability bounds, concentration of the regret, even just for the adversary case. And so then the question is whether people consider doing the analysis with that modification.
Yeah, I don't know when you get done. So the problem, even when you have this optimistic one, is that means when it's tuned to the adversarial case, it's already having again this square root T regret. And I'm not sure what happens if you set it smaller in the hope that, I mean, you to only have high probability bounds when the environment is nicer. I haven't seen anybody trying this.
On your early slides, you had the example with the weather changing every day.
Yeah.
Correlates away. Do we have a solution to this problem where there's no budget every day?
I mean, this is actually an example of something that now just falls under the stochastic setting, even though it's not I.I.D, because this was done in a way that whatever the context is, the relative goodness between each arms stays unchanged. And so here, it's, even if an adversary is choosing whether at any time step is rainy or sunny, this decomposition that I'm using at the end of my analysis, where I'm just saying, here up there, where say the regret is equal to the gap times the probability of failing. This equation there holds in that setting too, because whether the context is sunny or whether this gap is the same. And so we actually, for this example, we can even prove logarithmic regret for this argument.
More questions?
This might be a bit of a technical one, but I didn't understand something. So in your proof, in the end, you set the weights, which according to which you sample, such that the regret is minimized, right?
Yeah. Okay. So you're asking about this step that I'm doing here.
So is this then through the step then you get the weights for the algorithm? Is this?
Yeah. No. Unfortunately, no. So this is just saying what would be the worst case weights in terms of the regret analysis, but I don't know. I mean, the weights of the algorithm itself are going to be some random variables, and they're going to be somewhere. So this is just giving us an upper bound, but it does not, unfortunately, tell us anything about what is actually the true mean of these weights anyway.
There's no question, then let's thank Julian again. And the next talk will begin at 4 p.m.